For machine, how to draw a velocity triangle for a centrifugal pump. So in this video, I would like to share with you on how to draw a velocity triangle. A velocity triangle is a triangle that show a velocity on the blades. So it is very important for you to know how to draw the velocity triangle, because our calculation is based on this velocity triangle. Please follow this step by step, and I hope you could draw your own velocity triangle properly. So I hope you could remember a few simple steps that I will teach you here to draw the velocity triangle. It is depending on the shape of blade, and it is very important because a few equations need to be derived based on the velocity triangle. And also we have a few type of blade, so mean the velocity triangle will change according to the blade type. So it is not worth for you, it is not a good idea to remember. The important thing is you could draw your own velocity triangle depends on the shape of blade. So this is a few basic steps that you need to remember. One is you need to know how to draw the blades. And then we draw the absolute velocity. Then we draw the velocity components due to the rotational speed and blade curve. Then we draw the theoretical velocity and its component. And then we could determine the blade's angle and the flow angle. And then we could draw this triangle velocity triangle based on backward or forward or radial blades. First, you need to draw the blades. So it depends on the question, because as I said, we have three types of blades. One is backward, forward, and radial. So how to know which is a radial or backward or forward? The idea is simple. First, you need to know what is the rotational speed. Which direction of your rotational speed. So let's say we have a rotational speed that rotates from right to left counterclockwise like this. So and then means that if the rotational speed is counterclockwise direction like this, the water will also move at counterclockwise like this. Then if we have blade like this, you just imagine that you sit on the tip of the blade here and facing at the same direction of the rotational speed. Means that you just imagine that you stand on the tip of this blade and then you are facing to the left, because the rotational speed is counterclockwise. If the rotational speed is clockwise direction like this, so you just imagine that you stand at the tip of the blade but facing to the right. Okay, let's say we have rotational speed counterclockwise like this, and you imagine that you stand on the tip of the blade. Only on the tip of the blade, mean not at the inlet here but at the outlet here. Standing at the tip of the blades, and you are facing the same direction of the rotational speeds, mean you are facing to your left now. So if the blade here is facing backward, so we call this blade as the backward shape. If the blade is radial, means the blades here is 90 degree at the point you standing here, so we call that blade is radial. So if the blade is facing forward in front of you here, so means that the blade type is forward. So I will talking about this later, but first we need to draw the blades. It depends on the question whether it is backward or forward or radial blades. Then we draw the rotational speed. It is very important. And then we need to draw the boundary of the shroud. So we have, as we say, that the blade is on the impeller, on this shape, on the circular shape like this. So we determine that from the center to this line is the inlet radius, and from the center to this line it will become the outlet radius. So we mentioned the inlet radius as R1 and outlet radius is R2. Normally, subscript 1 will refer to the inlet and subscript 2 will refer to the outlet. Then, we determine the blade angle. The blade angle means the angle at inlet and the angle at outlet here. So, the idea is simple. Just we draw a tangent line here, and then we draw a line parallel with the shape of the blade, and then we determine here is beta 1. Again, at the outlet here, so we draw a tangent line here, and then we draw a line parallel to the blade shape here, and then we take the angle of this one, and we call this as beta 2. So this is beta 1 and this is beta 2. Beta 1 means the blade angle at inlet and the blade angle at outlet as beta 2. Next, so we leave about the blade angle. So this is a very important step. The first one, you need to draw the absolute velocity. What is absolute velocity? Absolute velocity means the actual velocity of liquid travel from the inlet here, the eye of the pump, to the blade area. So just imagine that if the rotational speed rotates counterclockwise like this, the absolute velocity will flow like this. It is not a radial direction, not from here to here. I will explain it later. So it will flow a little bit slanted from the radius here. So you just draw it's equal to V1 like this, and at the outlet the same direction to the inlet here, so from here to here, let's say. So we label the absolute velocity as V1 and V2. V1 means absolute velocity at inlet, and V2 here is the absolute velocity at the outlet. Next, we need to determine what is the angle of the absolute velocity. So it's very simple. We have a absolute velocity V1 here, and then we draw a tangent line to the circle here, and this angle is called absolute velocity angle, or the flow angle, means the angle of the water flow to the blade. And this angle, we draw a tangent line here, and this is V2 at outlet. So the angle here is labeled as alpha 2, means the flow angle at outlet. Then we need to draw two types of component velocity. Component velocity. One is component velocity due to the rotational speed and blade curve. So what it is mean? It is mean that, okay, for example, we have one molecule here just enter at the inlet of the blade like this. However, at the same time, the blade is moving counterclockwise because it's rotate on its own shaft. it's rotate counterclockwise, so mean the blades is now moving here. And then at the same time, this molecule will flow on the blade until this area, until at this location. So mean in one motion, there are two movements occur on this molecule. You just imagine that this molecule enter the inlet of the blade moves counterclockwise until this location, and this molecule is now at this area, at this location. So means that if we split the direction of motion of the fluid here, of the molecule here, we could say that this fluid, this molecule is moved along this circular line because the blade is moved parallel with the rotational speed. So it's moved from here to here. Then this molecule also move from here to here because there is a flow along the curve of blade. Means that this direction is influenced by the blade shape. So from this idea, we could say that the molecule that enters blade here will be influenced by the rotational speed and the blade curve. Means that we need to split the actual velocity into these two types of component velocity. However, for rotational speed here, as I described previously, the rotational speed here usually will be mentioned in RPM or rad per second. However, another velocity in the blade here will be mentioned in meter per second. So, we need to change the rotational speed from the rad per second into meter per second. So what we should do is we use this equation. U is equal R omega, and U is linear velocity in meter per second, and R is the radius. So if we calculate about the inlet, we use R1. If we calculate about the outlet, we use R2 here. And omega here is radian per second. If the pump speed is in meter per second, and is in RPM, rotational per minute, you can use the previous equation, U equal to R omega equal pi dn over 60. Then, this is our absolute velocity. The absolute velocity is the actual velocity. So means the actual velocity here, V1, is also can be imagined as the resultant velocity. So we have the actual velocity or the resultant velocity here in the inlet. Then we could split this resultant velocity into two types of component velocity, which is component due to the rotational speed, which is equal to U1 here, and the component that flow due to the shape of blade here. So we call it as R1. So we have U1 mean the tangential velocity at inlet, and the VR1 here, R mean relative, the relative velocity at inlet. So relative here means the relative velocity to the blade, and tangential means because it's moved in rotation in circular shape. So at this point we take the tangential velocity. So we draw a tangent line here and the velocity is here. So this is a vector. So you could move this arrow anywhere you like. For example, U1 here can be moved from here to here, and VR1 could be moved from here to here. Then we do the same thing at the outlet. So we have the V2 here, the absolute velocity, means the real velocity or the resultant velocity at the outlet. And at this point, we could draw a tangential velocity. Must be tangent of this point. So we could draw a U2 here, and it is similar to draw U2 at this line. Then we could draw the VR2, mean the relative velocity at outlet. So we draw VR2 here. And again, I would like to mention here, to draw tangential velocity, we need to draw a tangent at this point, and we draw the tangential velocity. Also at this point, we draw a tangent line, and we draw a tangential velocity parallel to the tangent line. And to draw the VR1, the relative velocity, we need to know what is the angle of the blade here. So if the blade is inclined like this, so it is okay for us to draw a VR1 here parallel with the blade shape at this point, at inlet. At the outlet here, VR2, it is okay for us to draw a VR2 here parallel to the line at the outlet here. This is an important thing because we believe that V2 and V1 here is the absolute velocity or the resultant velocity. It is important for us to make sure that the component velocity will create a closed loop to the resultant velocity here. So means that the VR2 must be from here to here, and then the U2 must be from right to the left. Then the velocity vector here will close loop the resultant velocity here. It also occurs at this point where this is the resultant velocity and this is the U1 and this is the VR1. Okay, now we forget about the U1 and VR1. We are focusing with another velocity component that relate to the theoretical. In the first session, when we draw the actual velocity V1 and V2, I asked you not to draw the velocity V1 or V2 here parallel with the radial. It is because the flow in theory, the flow will flow in radial, because this is what we learn in ideal flow. When you have a source, a water come from one single source like this, the water will flow in radial direction. So in theory, the water will flow in radial direction. So we could draw F1 like this, the blue arrow, and at outlet we could draw F2, VF2 like this, parallel to the radius here. Okay. However, in reality, we found that the flow will enter the blade with a little bit slanted like this one, like F1, like V1 here, and V2 here will come out a little bit slanted as V2. Okay, so why it's happened? Because it face resistance or it has losses. So means that in theoretical, the flow must be in direction of VF1 here, and it must come out in direction of VF2 here. But because of losses in blade and losses in this mechanism, the V1 will flow a little bit slanted, inclined like this, and V2 will be inclined like this. And then we could say that the losses, the velocity losses can be shown as VW2, and at inlet it can be shown as VW1. So we call this VF2 as flow velocity, means theoretical flow velocity at outlet, and Vf1 is theoretical flow velocity at inlet, and W is whirl, the whirl velocity at inlet and the whirl velocity at outlet. So mean the whirl mean resistant or turbulent that occur at the inlet and the outlet. So means that if the actual velocity can flow same direction of Vf2 here, so mean there are no turbulence occur at the outlet. Same goes to the inlet here. If the inlet velocity can flow same direction with Vf1, means there are no turbulent velocity occur. So mean there are no velocity of whirl at inlet and there are no velocity whirl at outlet. So again, because we assume that V1 and V2 here is the resultant velocity, so please make sure that your direction of V1 here is from here to here, and then the direction of Vf1 is from center to the inlet of blade. So this is the resultant velocity, so it must be closed loop. So this is the Vf2 here, and this is the V2. So these two velocity component must close loop the resultant velocity. Also here, they must close loop the resultant velocity. So then, I hope you could combine both velocity that we have. We have actual velocity V1 and V2. We have component velocity of VR2 and U2. And also we have velocity of VF2 and VWL2 in this outlet. And inlet is we have U1 and VR1, and we also have VWL1 and VF1. So this is the close up to the inlet velocity. Again, so this is the absolute velocity. And then this triangle is for U1 and VR1. And this triangle is for VW1, VWL1, and this is for VF1. So this is the close up to the outlet velocity. So this is the V2, the absolute velocity, the real velocity, and this is component of VR2 and U2 here, and this is the component of VF2 and VWL2.